Welcome to the third lecture in my series on grad div curl, the holy trinity of vector calculus. When I had first envisaged the series, I thought it would be a very quick one. One lecture each on the gradient, the divergence and the curl, and I will be done. Well, things turned out slightly differently. It turns out that the concept of divergence is complicated enough, and just to introduce it properly, we need to introduce further concepts like flux and so on. And so, I decided to split the divergence lecture up into two parts. In the previous part, we had formally defined what the divergence of a vector field A really is. Note that the value of the divergence of the vector field A at a point P is given by a limit. This is the limit of the ratio between the flux of the vector field A across a closed surface sigma, which is the boundary of a volume tau, to the volume tau itself. And finally, you take the limit as this volume shrinks down to 0, while of course still containing the point P in it. We had explained why we expect this limiting procedure to work out, why we also believe that the limit will be independent of the particular shape of the volume that we take, as long as the volume contains the point P and it does shrink down to 0. Also, by making use of Cartesian coordinates, we had explicitly calculated the divergence of a vector field A and showed that it is equal to this particular scalar field, del Ax del x plus del Ay del y plus del Az del z, which can of course be written down in a shorthand form as the del operator dotted with the vector field A. We had also taken a look at a few examples of situations where vector fields could be classified as those with or without divergence, and we had also seen that sometimes the issue can be a bit more complicated than what strikes the eye at first glance. The first task in this lecture is to actually go the other way from the definition of the divergence. In the definition of the divergence, what we had done was define divergence as essentially flux per unit volume in a limiting sense. The question is, can we reverse this? Given the divergence of a vector field, which is of course a scalar field itself, can we use it to figure out the flux of the vector field through any surface? Since divergence is, after all, a density of flux per unit volume, it should be easy enough to figure out the flux in the situation where divergence is a uniform scalar field. If divergence of A is uniform, then flux through a surface sigma, which is the boundary of tau, some volume, can be found simply by multiplying the volume tau by the value of the divergence of A. But what if the divergence of A is not uniform? What if it changed from point to point, as it would be the usual situation in most cases? Then you cannot multiply the divergence of A by a volume simply because you would not know which divergence to use. You would of course be multiplying by some average value of the divergence, but in order to find that average value, you would actually have to find the flux first and then divide by the volume. So the average value of the divergence would be rather useless in calculating the flux. However, this situation should be pretty familiar to us. There is another situation where you can easily find a physical quantity by multiplying by a volume. Well, the mass, for example, can be easily found by multiplying the mass density by volume, provided the mass density is a constant. What if the mass density is not a constant? Then what you would have to do is break up the volume into many tiny pieces, multiply each of the pieces by the volume of the piece, add up together, and then take the limit in which even the largest of the pieces went to 0 volume, so that in none of the cases did density get a chance to vary over the particular piece you were using. When you put all of this together, you get what is called a triple integral or a volume integral of density. It's easy to see that in this case too, a similar concept can be used. What you should do then is divide up the volume tau into many pieces. Delta tau 1, delta tau 2, delta tau 3 and so on. If you focus on any one of these pieces, let's say the ith piece as you can see in this picture, if you multiply this volume delta tau I by the value of divergence of A somewhere in this volume, you are going to get an approximate value of the flux across the surface bounding this delta tau I. Note that this is going to be approximate because if your volume is not infinitesimal, but some finite piece, no matter how small it is, there is going to be some variation of divergence of A in it. All I am doing is assuming that we have taken a piece small enough that this divergence will not vary very much inside that piece. Now when you add them all together over all the i's, what you get is, on the one hand, an approximation for the volume integral of divergence of A, which is an approximation because you are using finite small pieces. You have not yet taken the limit as the largest delta tau I goes to 0. This is also approximately at this stage before you are taking the limit, the sum of fluxes through all the faces bounding the pieces. Here it's an approximation again for the same reason. Because divergence of A could vary within the small region delta tau I, multiplying divergence of A at some point in this ith piece by the volume does not really give you the flux across the ith piece. But if you look at the sum, what you are going to get is there will be many pieces which have shared faces. Now, in the end, the flux is contributed by a face which is shared between two of these pieces will always cancel out. To see this, let's take a look at this picture of two pieces where, for simplicity, I have drawn two rectangular parallelepipeds sharing a common shaded face. The purple piece on the left, which has a contribution from this shaded face, for which you have to use the blue outward normal, which in this case is the outward normal as far as this piece is concerned. As far as the orange piece is concerned, the same shaded face will have to use the outward normal for this piece, which is the green one. So these two normals being equal and opposite to each other, the contributions of the shared face to both of these spaces come with a minus sign and they are equal in size. So when you add them all together, all of these shared faces will give you two contributions, one positive, one negative, and they will all cancel out. After all of these cancellations, what we are left with is a net flux across the outside boundary sigma of this region tau, and we have used here the notation del to indicate that this sigma is the boundary of this volume tau. Of course, as the outside faces are concerned, there is nothing on the other side to cancel the result out. So here, this result turns out to be equal to the flux across the outside surface, at least approximately. But note that the reason behind the approximation is the same for both sides. This is approximately the volume integral because you are using finite pieces, and this is approximately the sum of all fluxes because the flux through each piece cannot be exactly equal to divergence of A in that piece into delta t tau I unless the divergence of A is really uniform or unless the piece is very tiny. So when you take the limit in which the largest delta tau I goes to 0, so you take this limit then this becomes an exact result. Before that, this was really an approximation. But in this limit, this sum actually becomes exactly the volume integral of divergence of A d tau over the volume tau. And so we have finally arrived at a very, very important theorem, the so-called Gauss divergence theorem, which tells you that the surface integral of a vector field over the surface bounding some region del tau, of course this has to be a closed surface because it's bounding a region, is equal to the volume integral of the divergence of A over that region. This happens to be one of the most important theorems in mathematical physics and will turn out to play a very, very important role in applications in a wide variety of different fields. If you think about it, this proof of Gauss divergence theorem is really rather clever. All it does is that it turns the definition of divergence on its head, and rather than thinking of divergence as a limiting value of flux per unit volume, tries to figure out how to calculate flux through a surface starting from the divergence. Now this theorem itself is important enough that it merits other proofs as well. And I am going to explain to you another proof soon. And frankly, this proof is one which is more likely to be found in a standard mathematical physics textbook that you may consult. I am not saying that that proof is more robust or more rigorous than the proof that I have just given you. This proof is fine. It's just that another proof may give you another way of looking at things. But we must cover one thing before we even start getting into that proof. We spent most of the last lecture describing what a flux is and essentially talking about surface integrals and how to make sense of surface integrals. That is, by chopping up a big surface into tiny pieces and so on. But let me point out that if you were to actually try to evaluate a surface integral, then very often you will not really take the chop into pieces approach. This is very similar to the fact that you wouldn't really take the chop into pieces approach when you try to calculate an ordinary integral. You would usually use something called the fundamental theorem of integral calculus, at least when you're trying to evaluate the integral analytically. Now, as far as evaluation of a surface integral is concerned, a numerical evaluation, of course, would actually essentially use the chopping up into pieces approach. But any analytical evaluation of a surface integral would essentially need you to turn to the fundamental theorem of integral calculus, which unfortunately works directly only for ordinary integrals. So somehow you have to convert your surface integral evaluation into the evaluation which can ultimately use the fundamental theorem. What you do is a two-step process. You convert a surface integral into a double integral, which is like a surface integral, but you do it over a flat surface. Not like in general you would use a curved surface. And then when you are doing an integral over a flat surface, you essentially keep one of the variables describing the flat surface, let's say one of x or y, fixed, and vary the other, and then vary the strip over which you have integrated in the first step. So if you were to take a tiny rectangle bounded by x and x plus dx and y plus dy, vary only x first, keeping y fixed, what you would get is a horizontal strip. Now this integral is an integral over a single variable which you can evaluate, at least in principle, using the fundamental theorem. And once you have found this out, this integral is going to depend on y, and then you have to add up the contribution from all the strips to make up the overall region. This will be your second integral. That's why an integral over a flat surface is often called a double integral. You do first one integral, keeping one of the variables fixed, and then do the other integral. So, both of these integrals can be evaluated, at least in principle, using the fundamental theorem of integral calculus. But the first step, as we have said, would be to reduce the surface integral over a general curved surface into a flat surface integral, that is, into a double integral. Let me now describe how that process is done. In the picture on the left, what you can see is this surface sigma over which we want to do our surface integral. Note that while the integral that we do over the surface in Gauss divergence theorem is over a closed surface, surface integrals can of course be done over open surfaces as well. Surfaces which don't bound a region, like the surface in this picture. And we are really considering a special simple kind of surface here, one which can be uniquely projected down to, let's say, the xy plane. So this light blue curve here gives a boundary of the projection, where I project every point of this surface bounded by the deep blue line downwards onto this plane. R is a projection of sigma. What do I mean by unique projection? Note that this surface is special in the way that every point up here projects down to one point on xy. That's rather obvious. All you have to do is take the coordinates of the point xyz and replace that by another point down here with the same x and y coordinates, but 0 for the z coordinate. But the important point is, this one is the only point on the surface sigma which goes down to this point xy0. In other words, the surface does not fold back on itself like this. If it folded back on itself, then both of these 2 points would project down to the same point. We are assuming that that does not happen. We are considering a surface which has a one-to-one relationship with its projection. This one-to-one relationship is actually very important, because what we are going to do is we are going to next think of breaking up the surface into tiny pieces, and instead of thinking of these pieces, we will think in terms of their projections. Now we want to have this projection as one-to-one simply because when we go over the pieces down here, we want to ensure that every piece down here corresponds to a unique piece of the surface up here. And to make things even more simple for us, what we are going to do is we are going to actually back project, in the sense that we are going to take a rectangle. This may not look like a rectangle because of the perspective, but this really is a rectangle, bounded by x and x plus delta x and y plus delta y, that is with widths delta xi and delta yi. There is an ith piece, and look for the upward projection of that or inverse projection of that part of the surface sigma which projected down on this. Now if I break my region, the flat region R, into many such tiny pieces and then look for what pieces of the surface projected down on them, it's obvious that I'm going to get each and every piece of sigma once and only once as I run over every piece which this R is broken up into. This one-to-oneness is important simply because we want to keep track of every piece coming from this surface sigma. Next, what you need to do is, of course, multiply A dot n hat, the projection of A onto this normal to the surface delta Si, by delta Si. But remember, what we are going to do is try to convert this surface integral into a double integral over this region R. So instead of thinking of delta Si, we are going to think of this projected piece delta Xi, delta Yi. But the area delta Si is not the same as the area delta Xi, Yi. Right? This is delta Si up here, and this is the projection delta Xi, delta Yi. How are these two areas related? It's obvious that this area up here is actually slanted and hence bigger than this area delta Xi, delta Yi, and is slanted by an angle theta, which means to get the area delta Si, we have to divide by cosine theta. But we have to be careful. This works only as long as cosine theta, cosine of this angle, is actually positive. Now this angle could of course be both acute or obtuse, so cosine theta could also be negative, but this is just a ratio between areas, so what you need to do is use the magnitude of the cosine of theta. Now theta is the angle between this surface delta Si and the flat piece delta Xi delta Yi, but it's also the same as the angle between the normals. The normal to delta Si is of course the n hat which we used for this surface integral. The normal to this delta Xi delta Yi is simply the unit vector in the z direction, that is z hat. So you have delta Xi delta Yi, the area down here, divided by magnitude of z hat dot ni, the normal to the ith piece. So now, let's go back to our surface integral. The surface integral over sigma is simply nothing but this limiting value for the largest delta Si going to 0 of this sum a dot n taken on the ith piece times the area of the ith piece. Now if this surface area delta Si goes to 0, then delta Xi delta Yi, or the largest of them actually, also go to 0. So this limit, where the piece on the surface shrinks down to 0, is also the limit in which the projection down below shrinks to 0. That's all I'm saying. And what I've done is just rewritten this sum with a dot n from the ith piece, but delta Si replaced by delta Xi delta Yi divided by mod of z dot ni. Now this sum is nothing but the integral over this flat face R. So the double integral over dx dy over the region R of this quantity a dot n divided by mod of z hat dot n hat. One thing has to be very clear here. Although you are going to do the integral over the region R, the value of a dot n must be this value a dot n that you had here. So it should come from the value of a and the value of n from the surface sigma, not from the flat piece R. So the a used in this a dot n is not the a down here. After all, a is a vector field. It also has a value down here. It must be the value of a up here, because this is what we are really summing up. Similarly, z dot n hat, when you do that, you have to evaluate it from the surface. Of course, z is the same no matter whether you're doing it up there or down here. The unit vector in the z direction does not change. But n hat has to be the normal to the surface, not obviously the normal to this flat R. And that is what is indicated here with this sigma written on the side. We should remind you that while you are doing an integral over the region R, what you really are doing is integrating values of a dot n from the surface, and you have to divide by mod of z dot n with n taken from the surface, just to ensure that your surface area delta Si is properly accounted for. At the end of the day, what this allows you to do is to replace the surface integral over sigma to a double integral over R, which, as we have explained, can be evaluated, as we have explained, at least stepwise using the fundamental theorem of integral calculus. Now, all this may sound rather complicated, but it's actually rather easy to do in practice. I will give you one example of a non-trivial surface integral calculation soon. But before I do that, let me point out one thing. Very often the surface sigma is described as a surface which obeys some constraint. Some function phi of xyz is a constant there. Then of course the n hat vector, the unit normal, is proportional to the gradient of phi. It's actually the unit vector in the direction of the gradient of phi. Now, because n hat appears both in the numerator and the denominator of the formula, you don't really have to bother normalizing grad phi by dividing by mod grad phi. as far as this calculation is concerned, instead of n hat, you can just simply use grad phi. Because the normalization factor, the length of grad phi is simply going to cancel between the numerator and the denominator. But once again, it's very important to remember that the value of the gradient of phi and the value of the A has to be taken from the surface sigma, not from the region R down below. Let us now turn to the evaluation of the flux through a surface of a non-trivial vector field. Now, the example that I've chosen for you is the following. I'm asking you to calculate the surface integral A dot ds over sigma, where A is given by an inverse cube field, k r hat by r cube, and sigma is actually part of an ellipsoid described by the equation x square by a square plus y square by b square plus z square by c square equals 1 in the first octant. That is, in the region where x, y and z are all positive or at verse 0. Now, this picture is an attempt at depicting the surface of this ellipsoid. It's going to be something like this. It's a curved surface. Now, the ellipsoid, of course, intersects the x, y and z axis at A0, 0, 0, B0, 0, 0, C respectively. And what we need to do is evaluate this by projecting this surface down onto the xy plane. By the way, why use the xy plane? Well, that's simply for convenience. I could have used the yz or the zx planes as well and should have ended up with the same result, provided, of course, that you can project your surface down in a one-to-one manner onto the plane in question. In this case, my surface is such, this surface of the ellipsoid is such, that I can project it down to the xy or the yz or the zx plane without any overlaps. So any one of the projections would have worked. I've decided to project onto the xy plane, but that's simply my choice. On the other hand, if this had been the surface of the ellipsoid in the upper hemisphere, that is, the entire ellipsoid for z greater than 0, let's say, then it should be easy to see that you cannot really project onto the xz plane, for example. At least you cannot project it in a one-to-one fashion. If this entire region, that is all of it, was being used, then the part in front here would project onto this elliptical region in the yz plane. The part at the back would also project into the same elliptical region. So you could not use a projection onto the yz plane. For a similar reason, you couldn't use a projection onto the xz plane, because this portion in the front would project onto this elliptical region. The back portion would also project onto the same region. In this case, you can of course get away by projecting onto the xy plane, because every point on this half ellipsoid would project uniquely onto the xy plane. Well, what if you had the full ellipsoid? Then none of these planes would work as it stands. Then what you would have to do is perhaps divide the ellipsoid into two pieces. Say if you slice the ellipsoid down the middle, you get an upper piece for which you can do a perfectly nice projection onto the xy plane. For the lower piece, separately you can do another perfectly nice projection onto the xy plane, and then evaluate these two integrals separately. For the time being, we are just using the part of the ellipsoid in the first octant, so no such problems arise. As I said, I could have projected onto any one of the coordinate planes. I've just chosen to project onto the xy plane. But before even we do the projection, what we need is a formula for the normal n hat at a point on this surface. Now, the surface itself is defined by phi equal to constant. This function phi has a constant value 1 all over the surface. So for n hat, what we need is gradient of phi, which is easy enough to evaluate. Grad phi works out to be this. Indeed, I don't even need to bother about the 2 outside in this case, because that would also have cancelled between the numerator and the denominator. But for the timing, let's just keep this in. So if we take the A, which is k r hat by r cube, or k r by r to the 4, that is this expression, and dot it with the grad phi, what you get, still retaining the 2, is this quantity. In the numerator, you get x square by a square by dotting this with this, plus y square by b square, plus z square by c square. Of course, this means that this numerator is just 1, and you have ended up with 2k in the numerator, divided by x square plus y square plus z square whole square. But now, what we have to remember is we are going to actually do the integral over r. There, of course, z is 0, but you cannot use z equal to 0 in the integrand. In the integrand, a dot n hat, or in this case a dot grad phi, has to be evaluated on the surface. So while we are using x and y to denote points on the region R, the projection down here, I would have to take z value from the surface itself. That is, I have to replace the z square here by this quantity, c square into 1 minus x square by a square minus y square by b square. So this is my a dot grad phi, and k dot grad phi is even simpler. It's just going to be 2z by c square. So the region R over which the double integral should be evaluated is simply what this ellipsoid or the octant of the ellipsoid projects down to. And that's nothing but the region bounded by the x-axis, the y-axis, and the ellipse x square by a square plus y square by b square equals 1. But this is the region where x and y are all positive. So in the first quadrant. So now this surface a dot ds integral becomes the double integral over the region R of a dot grad phi by mod of k dot grad phi. In this case, k and grad phi point in the same direction. So the modulus is actually positive by default. Remember, k dot grad phi worked out to be 2z by c square, and z is positive in the first octant. So this is what you have to do. Evaluate dx dy over r of this integral kc square, x square plus y square plus z square whole square into z. The c square by z comes from the k dot grad phi, the 2 of course having cancelled. The important point that I have to drill in again is that while I have written this as a double integral over r, the value of z has to be taken from the surface. You cannot simply replace it by the value on the region R. Of course, that would have been a disaster, because on the region R, z is 0, so this would have given us an infinite integrand. What it actually does is gives us this integral. If you look at the integrand, you have kc square by x square plus y square plus c square into this whole thing, and z has to be replaced by c into the square root, and 1c cancels out. What about the limits of the integration? If you want to do the integration in Cartesian coordinates, you have to hold one of the variables fixed and then integrate over the other. Here I have decided to do the y integral first, so I have to hold the x fixed and let y vary from 0 to whatever value it can go up to for a particular value of x. The fact that the region is bounded by the equation x square by a square plus y square by b square equals 1 tells me that the maximum value that y can go to up to a particular value of x is simply the upper limit here, b into square root of 1 minus x square by a square. Now that we have done the y integral, we allow x to go over its entire range, which is from 0 to a. Of course, you could have done this in the other order, over x first and then over y. But if you had done it over x first, then x would have gone from its lowest possible value, which is 0 for our region, to its highest possible value for the given value of y, which would have been a into square root of 1 minus y square by b square. And after that, you would have taken the y integral with y ranging from 0 to b. So now, what we have done is we have reduced our surface integral to a standard double integral which we can evaluate in principle. It may not be very easy to evaluate this integral as it stands. Frankly, going over to a version of polar coordinates where x is given by ar cosine theta and y is given by b times r sine theta would make your evaluation slightly simpler. But even then, the final answer can be figured out only in terms of some rather non-standard functions called elliptic integrals of the first and second kind. But evaluating this particular integral was really never our intention. My intention here was to show you how you would replace a surface integral by a corresponding double integral, which helps you to calculate the value in the end. I hope this example has been clear enough for you to follow the general procedure. With this idea about how to evaluate surface integrals under our belt, let us use this to provide another proof of the Gauss divergence theorem. First, let us focus on the surface over which we are going to do the surface integral on one side of the divergence theorem. This surface sigma is a closed surface. And the problem with a closed surface is, no matter which plane you try to project it onto, you will always get overlaps. Say here, this piece here and this piece here would project down to the same piece of the xy plane, namely the piece marked there, dx dy, down here. So you cannot directly use our surface integral evaluation method as far as that is concerned. What we need to do is that we have to break this surface sigma up into pieces. Here I am making an assumption that this is a simple kind of surface where if you slice it into two along its largest cross section, so to speak, it's going to split into two neat pieces, sigma 1 and sigma 2 in the picture, each of which can be projected down 1 to 1 onto this region R down here. So we have to evaluate the surface integral over the entire surface sigma by breaking it up into two pieces. Now what this really means as far as the equations governing these two surfaces is the following. If you look at a particular point xy down here in this region and look upwards until you hit the surface, you are going to hit the surface at two different points. That's why you needed to break it up into two pieces. If it had been more than 2 points, that would happen for a non-simple surface, then you would have to break it up into more than 2 pieces. For the time being, let's stick to this. Now, that means that the upper surface sigma 1 will have a unique value of z, which is described by a function f1 of x comma y. Remember, a function can only return one value, which is why you cannot describe the entire surface sigma by writing z as a function of x and y. But you can do it for the upper surface because there's only one point for a given value of x and y. And similarly, the surface below can also be described by using a single function, but this function will have to be called f2 of xy. Of course, each of these surfaces have their own normals, n1 up here and n2 down here. One thing is very important. N1 makes an acute angle with z hat. So the mod of z hat dot n1 will simply be z hat dot n1, whereas the mod of z hat dot n2, which you need to convert your surface integral into double integral, will have to have a negative sign. Let us now turn to the other side of the Gauss divergence theorem, which involves the volume integral of divergence of a vector field. Now that involves integrating over the volume tau with respect to dx, dy, dz, the divergence of a. Let us just take a look at one piece of that integral, which involves del az, del z. Now this volume integral can be thought of as one in which you do the integral over z first. Then you are going to do the integral over x and y. Now when you do that, z can of course go for a particular value of x and y from the point here, from here all the way up here. That is from f2xy as a lower limit to f1xy. Of course, after you do the z integral, you have to do an integral over x and y. And in order to get the entire volume, you have to let x and y range over this region R. So that is why a double integral has to follow this integral over z. This is a double integral over R. Now this integral is very easy to work out. Remember, as far as this integration is concerned, x and y are held fixed. So del Az del z is effectively the same thing as dAz dz. X and y not changing anyway. So this is really the integral over the change in Az, dAz. So this boils down to the integral from z equal to f2 to z equal to f1 of dAz. That is simply this integral, where you have to substitute the value of f1xy for z to get one end of the integral and subtract from that the value that you get when you substitute z equal to f2xy. In other words, this is what your volume integral boils down to. We have not completed the volume integral here, of course. We have just calculated the integral over z, which has changed the volume integral to a double integral now over the region R. Now let us take a look at each of these terms in some detail. The first of these terms, dx dy az xy f1 xy. Now just because of data convenience, what we have done is thrown in this factor. This of course is just 1. Multiplied by z hat dot n1, the normal up there, and divided by z hat dot n1. But notice that if we now push this z hat dot n1 along with the dx dy, what we have is dx dy by mod of z hat dot n1. After all, z hat dot n1 for the upper surface is positive, so it's equal to its own modulus, times az z hat dotted with n1, where you have put z equal to f1 of xy. That is, you have used values from the upper surface sigma 1. Now this thing is nothing but the area of a small piece of sigma 1, as we have seen before. And this is the value of azz dot n on the upper surface. So this is nothing but the surface integral over sigma 1 of azz hat dot n1. Now what about the second piece? The second piece is very similar, and I have just thrown in a z hat dot n2 by z hat dot n2 again. Here, there's a minus sign here. But note that now that I take the z hat dot n2 under dx dy as a ratio, the minus sign allows you to use the modulus here, which means this again is a surface area element, but this time the surface area element on sigma 2. And notice that we again have azz hat dotted with n2, the normal on the lower surface, but here wherever there is z, we have to put z equal to f2xy, the value it takes on the lower surface. Which means this quantity is being evaluated on the lower surface. And this is of course the area element of the surface itself. And therefore, this is again a surface integral, this time over sigma 2 of azz hat dotted with n2, the normal to the lower surface. The minus sign here, notice, has been absorbed into the modulus. So overall you have a plus sign as far as the surface integral is concerned. When you add these two things together, you essentially get the surface integral of azz hat over ds vector, which is ds n1 hat over sigma 1, and ds vector, which is ds n2 hat over the lower surface over sigma 2. And when you add them together, you simply get the total surface integral of azz hat dotted with n hat over sigma, which is the union of sigma 1 and sigma 2, the overall surface bounding the region. This tells us that the volume integral of del Az del z is actually equal to the surface integral over the closed surface bounding my region of azz hat dotted with ds vector. Now going back to the original picture, notice that here we had projected down onto the xy plane to get this region R. This is what helped me to actually convert this volume integral into a double integral over R and a single integral over Z. We can do something exactly similar for the del AX del X term, but there of course integrating over X first would be useful, which means that what we will do is that we will project this surface now onto the YZ plane. Again, you cannot project a closed surface in a one-to-one manner onto the YZ plane. You will have to divide it into two pieces. And a very similar thing will happen again for the del AY del Y's integral. There an integral over Y first would simplify matters. So I would have to project onto the XZ plane, and once again I would have to break up my volume into two pieces, maybe by a boundary like this, and project separately. By the way, I am saying two because that's the simplest possibility. Sometimes you may have to project into more pieces, but it's very easy to show that the final result will work nonetheless. So for each of these cases, what you will get is something very similar. Just like del AZ del Z's volume integral turned out to be AZZ hat's surface integral, del AX del X's volume integral will turn out to be AX X hat's surface integral, and so on. Adding all of these together, we get back the Gauss divergence theorem, that the divergence of A integrated over the volume tau is actually equal to the surface integral of A dot ds vector or A dot n hat ds over the surface sigma, which bounds the volume tau. This of course is important. This sigma is not independent of tau. It's a surface which bounds that region. Now that we have given you two different proofs of Gauss's divergence theorem, I am sure that you are pretty convinced that this is actually true. Is this useful? Well, for those of you who have studied mathematical physics or electrodynamics or gravitation or in fact almost any other subject in physics which deals with extended objects, you would realize that this is a very, very useful theorem indeed. I am not going to go into the uses of this theorem simply because that's not what I want to talk about here. I'm just talking about the mathematics behind all of this. But I'm pretty sure in your physics studies throughout you will meet many applications of this divergence theorem. Let me wrap up today's lecture by returning to the divergence proper once again. But this time talking about how to evaluate the divergence in other coordinate systems. We had seen in the last lecture that evaluating the divergence in the Cartesian coordinate system justifies the notation del dot A, because divergence in the Cartesian coordinate system simply becomes del x acting on AX plus del y acting on AY plus del z acting on AZ. The expression for divergence of A which we have just used in our proof. However, the first proof hinged on the actual definition of the divergence, which is flux per unit volume for a tiny volume. The limit of this ratio actually, the limit in which this volume shrinks down to zero. And we had already established that the actual shape of this region does not matter when you finally take the limit. So when we are going to evaluate expressions for the divergence in other coordinate systems, I am going to take regions which are convenient to describe in those coordinate systems. Let us make a start with the spherical polar coordinate system. The region that's easiest to describe in spherical polar coordinates is that bounded by r and r plus dr, theta and theta plus d theta, phi and phi plus d phi. As we have explained when we were talking about the gradient in the first lecture of this series, if r is changed to r plus dr, the point described moves to a distance dr, whereas when theta is changed from theta to theta plus d theta, it moves through r d theta, this length, and when phi is changed to phi plus d phi, it moves to r sin theta d phi. Strictly speaking, what we should have done is started with finite but very small changes delta r, delta theta and delta phi, and then gone on to take the limit in which delta r, delta theta and delta phi shrinks down to 0. But I am using infinitesimals with the idea that this will convey to you that we are going to take the limit in the end anyway. And especially in the infinitesimal limit, this region actually becomes a rectangular parallelepiped. Note that these three lines are actually at 90 degrees to each other, and so are all of these faces. Of course, for a finite change delta r, the upper face would be slightly bigger than the lower face, which is going to be very important in what is going to come. Now, we want to calculate the net flux through the faces bounding this region and then divide this by the volume contained inside the region. And then finally take the limit, which I've already implied in the notation dr, d theta and d phi. Just as in the Cartesian case, we are going to do this in pairs. We are going to first look at the flux to the pair of faces which are normal to r hat, which is this face out here and this face down here. Now, here, AR is going to be the component of vector A in the direction of r hat, of course. And the flux to the pair of faces is given by A dot r hat, A dot the normal, which is of course AR, times the area of this face. The area of a face here is given by r square sine theta d phi times d theta. This of course has only one d phi and not d theta d phi. The area is r square sine theta d theta d phi, and you are multiplying that by AR, the projection of A onto the normal to this face. That's the contribution from this face. From the other face, you have essentially the same contribution but with a minus sign. Minus, remember, because the normal which you should use for the lower face here is the outward normal, this one. That's why the minus sign comes about. But these two terms don't really cancel each other for the same reason that they did not cancel in the Cartesian case. These two are being evaluated at different values of r. R for this and r plus dr for this. Again, to be more careful, we might have said r minus delta r by 2 for this and r plus delta r by 2 for this. You should easily convince yourselves that that will not make a difference in the final limit. The one major thing that makes the formula for divergence in spherical polar coordinates different from that in Cartesian coordinates is the fact that when you go from this face to this face, it's not only AR which changes, it's the area of the face which also changes, as evidenced by the factor r square here. Which means that the difference here, which would have been del x ax into delta x for two faces normal to the x hat direction, in the Cartesian case, becomes del r of AR r square times dr times, of course, sine theta d theta d phi, which is a common factor. And therefore, this becomes 1 by r square del r AR r square. I've deliberately written the 1 by r square here because that leaves me with an r square factor out here and gives you exactly the volume of this region, which is given by r d theta times r sine theta d phi times dr. So that's the volume which you have to divide by in your calculation for the divergence. Now let us go on to the faces, the pair of faces normal to theta hat. There you have faces which are like this and they have lengths of dr and r sine theta d phi respectively. So the area of this face is r sine theta dr d phi. And once again, this face contributes with a positive value because you have to use the outward normal. This face, for which you have to use this normal, again the outward normal, contributes with a minus sign because that's against the theta hat direction here. So you get a theta times the area here and minus a theta times the area here. Once again, two things which look like they cancel but they don't. One being evaluated at theta, the other at theta plus d theta. And once again, the fact that the two areas are actually different becomes important. So del del theta of a theta is not what you get. You get del del theta of a theta sine theta here, with a d theta coming in from the Taylor series expansion of the difference. And r dr d phi just are factors which come in for the ride. Once again, if you want to take out the volume interval out here, which is r square sine theta dr d theta d phi, you have to divide by an r sine theta in this case. And finally, the flux with a pair of faces normal to phi hat is straightforward. Two faces with size a phi r dr d theta for this one, and a phi r dr d theta with a minus sign contribution to the flux from the other one, evaluated at phi plus d phi and phi respectively. Here only a phi changes from face to face because these two faces are equal in area. They are r dr d theta, they are the same in phi and phi plus d phi. So you just get del a phi d phi times r dr d theta. Once again, with the volume measure taken out, you get 1 by r sine theta as an extra factor. Putting them all together, flux through all six faces is this volume d tau times the sum of these three terms. And of course, to find the divergence, what you need to do is divide by this and take the limit in which dr d theta d phi goes to 0, which is a limit we have already implied, which is why we have not written down any higher order terms. It is these higher order terms which we had not written down which will cancel or which will go to 0 in the limit in question, and this will give us this formula for the divergence of A. Certainly a more complicated looking expression than the expression that we had for Cartesian coordinates, but it's really not any more difficult to understand. These terms look a bit more complicated simply because along with the components of the vector field, the areas of the faces of your region also changes as you change your coordinates. This latter thing did not happen in Cartesian coordinates, which is why you only had rates of change of ax, ay and az in the expression of divergence of A. I will leave the task of finding out the expression for divergence of A in cylindrical polar coordinates as an exercise for you, and move on to the general orthogonal coordinate system, which remember are situations where if you were to change any one of the three coordinates of a point slightly, will move in three different directions, and these directions are always perpendicular to each other. Now when you do that, you get a picture which is very similar to the picture we have already used, but this time when you change your coordinate q1, you are going to move through h1 dq1, not necessarily just through dr. Of course, for spherical polar coordinates, h1 is simply 1. For the second coordinate, if you change it through q2, you're going to move in this direction and through a distance h2 dq2. For spherical polar coordinates, this was the case where h2 was r, so you move through r d theta. And h3 dq3 is a displacement that you incur if you change q3 alone, and these three displacements are perpendicular to each other, which is the essence of a general orthogonal coordinate system. Working out an expression for the divergence in this case follows exactly the same lines as the one that I have described for spherical polar coordinates earlier. You have to actually calculate the net flux through all the six faces here, and for example, if you were to look at the faces which are normal to the surface of constant q1, that is these two faces, this face will contribute with a plus sign because this is the outward normal. This one, for which this is actually the inward normal, will contribute with a minus sign. And following the same procedure, you would simply see that what you will need is the derivative with respect to q1, which is the thing which changes between the two faces, of not only the component a1, but a1 multiplied by h2, h3. This is of course coming from the fact that the area of this face also changes when you move from here to here. So basically, if you were to calculate the flux difference between these two faces, and I urge you to try doing it yourselves, what you are going to get is del del Q1 A1 H2 H3 times dQ1 dQ2 dQ3. Now, since what you need is to divide this by H1 H2 H3 dQ1 dQ2 dQ3, you will have an overall factor of 1 over H1 H2 H3 outside. A very similar expression occurs for the other two terms. In this case, of course, if you have found out the result for one pair of faces, the result for any other pair of faces is very similar. All you have to do is permute the indices 1, 2 and 3 and get all the three terms. Indeed, this is actually a simpler case to work out than, say, the spherical polar coordinate case, where each of the faces were somehow different. But in this particular version, they essentially are all the same. So your final task that I will leave you with before I close this particular lecture is use this expression for divergence of A in general orthogonal coordinates to derive the equation for dA in spherical polar coordinates once again. And if you have also worked out the result for cylindrical polar coordinate system geometrically, then repeat that using this expression. Your job is going to be a lot easier or a lot faster in this case. But I would urge you to think about the geometrical picture every time, because that is what really hones your understanding of what is going on when you're using the divergence. In the next lecture, we are going to meet the third member of our Holy Trinity, the curl, and see how you can combine that with gradient and divergence to form new things.